So in this video, we're going to talk about 5.1 in our book. It's logarithms. So to kind of motivate this a little bit, let's think a little bit about what we know about exponentials. And I'm just going to pick one that we're probably more familiar with, y equals 2 to the x. So we know y equals 2 to the x is an exponential growth function since the base is bigger than 1. We know it's going to contain the point 0, because when you put in 0 for x, 2 to the 0 is 1. We know as we go to the right, it's going to bend up, and as we go to the left, it's going to approach the x-axis. So y equals 0 is a horizontal asymptote. We can see the domain is going to be all real numbers, and the range is going to be y strictly greater than 0. So we also know from what we've talked about before with inverse functions that this y equals 2 to the x is what we call a one-to-one function. So that is, for each value of x, there's only one value of y, and for each value of y, there's only one value of x. We would say this passes the horizontal line test, right? No horizontal line will intersect this graph in more than one point. So that means it must have an inverse, and the inverse is going to be a function. Now, if we try using what we know about inverses, if we switch that point, that 0, 1, then we know that our inverse is going to have to contain the point 1, 0. Since we can see that our original function 2 to the x has a horizontal asymptote of y equals 0, then our inverse function must have a vertical asymptote at x equals 0. If you can kind of visualize, if you wrote that yellow function in really wet ink and folded on that dotted line, I think you would see that it's going to look something like this. And that is, in fact, our inverse. So this function in green is the inverse of 2 to the x. And the question is, what should we call it? And, of course, as you know from your Algebra 2 days, this is a logarithm base 2 of x. So a logarithm base 2 of x is an inverse of an exponential y equals 2 to the x. So we can see also, because it is an inverse, that its domain, their domain and ranges get switched. So the domain of the inverse function, a logarithm, will be the same as the range is of the original function 2 to the x. And likewise, the range will be the same as the domain was for the original. Now, we have this fundamental relationship between logarithms and exponentials. And this is really key. You have to know this. So the logarithm, we say base b of x is equal to y. So there's our logarithm equation, y equals log base b of x. That is equivalent to the corresponding exponential. B is the base raised to the y equals x. So this is fundamental. We have to be able to go back and forth between a logarithmic equation and an exponential equation. So if, for example, if we say that 10 to the second is equal to 100, which is true, that's an exponential equation, then you can convert that to the corresponding logarithmic equation, something where these all mean the same thing. It would be the logarithm base 10. So the base of the logarithm is the same as the base of the exponential. We would say of 100 is equal to 2. So again, I will say this many times before we're finished. What is a logarithm? A logarithm is the exponent. It is that exponent that you raise 10 to in order to get 100. Okay, now let's go the other way. So I'll give you a logarithmic equation. And you can see if you can convert that to the corresponding exponential. So I'll say a logarithm base 16 of 8 is equal to 3/4. So that, which is a true statement, we should be able to convert to the base of our logarithm is going to be the base of our exponential. What the logarithm is equal to, that logarithm is an exponent, and that will be equal to the 8. And that is a true statement. So I'm going to go to a new screen, see if we can solve these without a calculator. So let's see if we can solve without a calculator. So I'm going to pause this for a minute so I can get them written down so it'll be more efficient. Okay, so here are some problems, and what I'm going to do is I'm going to go across and work the white ones, then the yellow ones, then the green ones. We're going to be using, of course, this relationship that we're going to convert a logarithm into an exponential and then try to solve it from there. So we read this as the logarithm base 2 of 32 equals x. We convert it to the corresponding exponential. 2 to the x is equal to 32. Now, because we're going to do this without a calculator, that means we must be able to write both sides of the equal sign as exponents with the same base. So if you count, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. We have 2 to the x is equal to 2 to the 5th. Therefore, x must be 5. On the second one, we'll go 3 to the negative 4 equals x. That's our corresponding exponential. Now we just have to know what to do with those properties of exponents. That's going to become 1 over 3 to the 4th. And if we have 4 3's and we multiply the first two and the last two, 3 times 3 is 9. Another 3 times 3 is 9. The 9 times 9 is 81. So that's going to be 1 over 81. And the third one, we have x to the negative 4/5 is equal to 16. These might sometimes give people the most trouble. So what we're going to do now is we're going to raise both sides to the reciprocal power. So we're going to raise both sides to the negative 5/4 power. So now when we take negative 4/5 times negative 5/4, that's going to cancel and just be x to the first. Now, however you want to solve this, I'm a believer in writing that as the power of the smallest thing that I can. So 2 to the 4th to the negative 5/4. When you raise a power to a power, we multiply exponents. The 4's are going to cancel, so we'll get 2 to the negative 5. The negative part of that exponent will make it into a fraction, and 2 to the 5th is going to be 32. And so we're going to get x is a 1 over 32. Okay, let's try the next one. We have square root of 5 raised to the x equals 1/25. And again, if we can do this without a calculator, we must be able to write both sides of the equal sign as powers with the same base. Square root of 5 is 5 to the 1/2, in turn raised to the x. This is 1 over 5 to the 2nd. When you raise a power to a power, we multiply the exponents, and 1 over 5 to the 2nd is 5 to the negative 2. So that means we can drop the powers, the bases, and say 1/2 x is negative 2, multiply by 2, and we're going to get x is a negative 4. The next one, we are going to get 16 to the negative 3/4 is equal to x. And again, you can do this a couple of different ways, but I'm going to write 16 as 2 to the 4th. When you raise a power to a power, we can cancel those denominators. When we multiply them, we'll get 2 to the negative 3, which is 1 over 2 to the 3rd, which is 1/8. And so we're going to get x is equal to 1/8. The third one, we've got x to the 3rd is equal to 1 over 125. We're going to raise both sides to the reciprocal power. So we're going to raise that to the 1/3 power. So the 125 is 5 to the 3rd, and I'm going to call that 5 to the negative 3. In turn to the 1/3 power, we'll multiply those exponents and get 5 to the negative 1, which is 1 over 5 to the 1st. And let's see, then we're going to let me change colors on my pen here. So we're going to say 27 to the x is equal to 9. And again, we're going to trust that we can write both sides of the equal sign as a power with the same base. When you raise a power to a power, we multiply those exponents, and then we can drop the bases and set the exponents equal to each other on our way to getting x equals 2/3. In the next one, we're going to get square root of 7 to the negative 2 is equal to x. Square root of 7 is 7 to the 1/2, in turn raised to the negative 2, We'll multiply those exponents, and that will become 1/7. And the last one, x to the negative 4, is 1 over 49. So we're going to raise both sides to the reciprocal power. So I'm going to raise both sides to the negative 1/4 power. And so that's going to become just x. The 49 is 7 to the second. And we can write that as 7 to the negative 2, in turn raised to the negative 1/4. Now this isn't great, but the negatives will cancel. The 2 will cancel with the 1/4. So we're going to get 7 to the 1/2. And so we can write that as the square root of 7. Okay, on to a new panel here. And let's see if we can talk about what we know as common logarithms. So we make sure we understand this vocabulary. This logarithm base 10 is used an awful lot because our number system is base 10, and so we can write that without having to write the subscript at all. So when we see that log of x, we know that's a logarithm base 10. Likewise, as we will see a lot next year, a natural logarithm is going to be a logarithm base e, Euler's number, of x, and we'll write that as ln x. So that's understood, that natural log of x is understood to be a logarithm base Euler's number. So we have some of these things. We know that the log any base of 1, because remember, a logarithm is an exponent, so this is 10 to what power is 1? Well, it's going to be 10 to the 0, so that means the log of 1 is going to be 0. The logarithm of 10 is going to be, remember this is now unwritten 10 for the base, 10 to what power is 10, and that means we're going to get 1. So the logarithm base 10 of 10 is 1. Sorry, bumped that with my hand. So I got to get my pen back up now. So our logarithm of 100 is going to be the log of 10 to the second. And so again, we're saying 10 to what power is 10 to the second, and that means it's going to be 2. And in the case of a natural logarithm, if we have the natural log of 1, so I'll call that x for a minute. Again, we have e to what power is 1, and it's going to have to be 0. So as we saw with a common logarithm, the natural log of 1 is just 0. The natural log of e, remember this is e to what power is e to the first, that's going to be 1. So the natural log of e is 1. The natural log of e to the second is going to be e to what power is e to the second, that's going to be 2. So the natural log of e to the second is 2. So in general, if we have the logarithm, any base of b to the x, these will cancel and we'll just get x. And likewise, if we have b raised to a logarithm base b of x, this exponential base b and logarithm base b are inverses. That's going to give us just x. So let's talk about some properties of logarithms. There's really only 3 that are of much importance, properties of logarithms. So the first one is the logarithm, any base of 2 things that are being multiplied, is going to be the sum of those logs. And the second one is the logarithm, any base of a quotient, a division of those 2 things, is going to be the difference in the logarithms. Subtract the logs. And of course, the big one is a logarithm, any base of a power. You can bring that exponent out in front and call it n times a logarithm base b of x. Okay, now a couple of misconceptions. So let's look out for these things. So these are things that are not true that people want to try to say are true. So be on the lookout for that. The logarithm of a plus b is not, and I emphasize is not, the log of a plus the log of b. So you can't somehow distribute that logarithm. The log of two things that are being multiplied is not the product of the logs. It's not log A, log B, right? We talked about that over here. It's the sum of the logs. There's nothing you can do with a logarithm of a sum. And we know the logarithm of A divided by B is not equal to the log of A divided by the log of B. We saw that property over here. It's the difference in the logs. And another one people sometimes try to say is the log of 1 over A. This is not the log of 1 over the log of A. Not true. Okay? All right. Let's see. Anything else we want to do? I think that's the big part right there. Very good.